Welcome to Xamarin University. This session is XAM150, Consuming REST-Based Web Services. Please be sure to download the class materials from the Xamarin University website. In this class, you will learn about the various device connectivity options there are and how to check for the device's connection type programmatically in your mobile app. You will also learn how to connect to various web services to retrieve and update data that's stored on a remote server. We'll start in Objective 1 by exploring the various connectivity types that a device may use to establish a network connection, and how you can determine if the device is currently connected to a network, along with the connection type the current device is using. We'll move on to Objective 2 and go through a brief introduction of REST services and how you interact with them. In Objective 3, we'll examine how we can make use of the device's network connection to communicate with a remote REST-based web service to select, insert, update, and delete data hosted within a server-side database. And then finally, we'll take a short stop and talk about how to optimize and tune your network access code for the platform. By the end of the class, you will know how to determine if a device is connected to a network and the type of connection the device is using. You'll also know how to efficiently connect to and communicate with REST web services to retrieve and manipulate server-side data. Our first step is to figure out the type of network connection the current device is using, if any at all. We'll discuss what the various connections options are for a mobile device and how we can programmatically check to see which connection type the current device is using. We'll also discuss how to monitor for network connection changes within the app. To start with, there are three things that you will be concerned with knowing about your network connection. First, you'll want to know the type of connection. Often on mobile devices, we have different network types that we can connect to, such as cellular, Wi-Fi, and sometimes Ethernet over USB. Next, you'll want to know the network status. Are we connected to a valid network? Will that change while the app is running? Can I initiate a connection and turn the cellular radio on? And finally, you might possibly want to know the cost of using the network. Are we roaming or on a metered connection? We can get all three pieces of information most of the time, but it will require that we do a little platform-specific logic. So let's look at all three cases. First, we should always check for network connectivity before attempting to perform network operations. This allows us to predict failure before it happens, and also to prompt the user to let them know that a part of the application functionality is unavailable, or perhaps that the application can't run at all without a valid network. On Android, we do this through the Connectivity Manager API. Connectivity Manager allows you to monitor the network connections, attempt to connect to other networks when connectivity is lost, provide notifications when network connections change, provide information about the state of the available network connections, and provide information about the connection status and the connection type. On iOS, we can use the built-in Network Reachability class. However, it's a bit painful to work with, so there's a nice wrapper available in the reachability sample on our developer.xamarin.com site, which makes it much simpler. The sample is available at the link shown on the slide here and in the materials you downloaded from Xamarin University. The reachability library was developed by Miguel de Icaza to provide a set of helper classes based on an existing Apple sample with the same name of reachability. This sample is open source. It's on GitHub in our MonoTouch samples repository. And this code allows you to monitor network connections, provide information on the type of network connection that is available, and provide information on the availability of external websites or web services. On Windows Phone, we can use the static Device Network Information class to grab the current network information. This provides information about the state of the current network connection, as well as providing notifications when the network availability changes. It also provides information on whether the user has enabled cellular data, or roaming data, or Wi-Fi. Along with knowing the current network state, your app will also want to track when that state is changed. Mobile devices are mobile, and as such, they move around while our apps are in use. So when the app is launched, we might have a great network connection, and then the user enters an elevator or a subway, and all is lost. The provision for monitoring the network connection is very similar to detecting the connection state itself. Android actually broadcasts a message when the network state changes, and you can register a broadcast receiver to get the notification in your app by registering an intent filter as shown here. This code then raises a static event which your app could hook to track state changes. Let's step through the code. First, we need to create a broadcast receiver class. This is indicated by decorating the class that derives from broadcast receiver with a special attribute. This will then add all the necessary manifest registration code to hook up the receiver. Next, we add an intent filter attribute to indicate which message we want to watch for. In this case, it's the connectivity changed message, which is a broadcast system message. Xamarin Android has a nice constant you can use for this. And finally, we override the onReceive method, which is called when the message is detected. This retrieves a Boolean from the past intent, and it raises the static event, which will then let the rest of the application know about the change. On iOS, we again will use the reachability sample. It exposes a single event, which is raised when the connection state has changed. Again, the link to the sample is on the slide here and in your copy of the materials. Finally, on Windows Phone, we need to hook two different static events. The first is used to notify our app when the network state changes. For example, if we are suddenly disconnected from the network because the user put the device in airplane mode. The second event is used when the assigned TCP/IP address changes. And this can happen if we connect to a different Wi-Fi network, or if we switch from cellular to Wi-Fi. The next piece of information that we might want to track is the type of network that we're on. Mobile devices often have several different network types they can connect to. We have a cellular connection, and this is typically a metered connection. The data is transferred across the mobile carrier network to and from the device. The carrier can modify the data to compress it. For example, images are often compressed. There are also additional costs incurred when data usage exceeds the data limit defined by the mobile carrier's data plan. We also have a roaming network connection. This is a metered connection, just like the cellular connection. The data again is transferred across the mobile carrier network to and from the device. Here again, the carrier can modify the data to compress it, and we have additional costs when the data usage exceeds the data limit defined by the data plan. And we have, of course, the Wi-Fi network connection. This is a wireless local area network. This is usually set up in homes and offices, or available in many public places, coffee shops, airports, restaurants, etc. Using Wi-Fi reduces the data on the cellular network and saves money. The user has to explicitly connect to a Wi-Fi network. Keep in mind that devices may restrict the types of connections available, so never assume you know what type of network you're on without verifying it first. Now, you care about this information because it changes the speeds at which you can communicate. Here are some examples. All three dominant mobile platforms have specific APIs you can use to detect the network type that you're connected on. For example, you can use this information to let the user know that something's going to take longer than expected if they're on a slow network. Again, detection of this information is platform specific. On Android, we'll use the network info class to determine the current network type. And this is retrieved from the same connectivity manager through a property as shown here. On iOS, we will again defer to our friendly reachability sample. But keep in mind, this class is open source, so you could take the code from it if you really wanted to, and just include it directly in your application. We'll use a few methods on the class to determine the network connection type. Again, cellular, Wi-Fi, or no availability. And then on Windows Phone, you can look at the network interface list and find the connected interface, which then gives us the additional information about the interface type. And this includes details about whether it's Edge, 3G, LTE, or Wi-Fi. The last piece of information you might be concerned with if your app is data intensive is the roaming state. On Windows Phone and Android, the application can detect if it's on a roaming network. In other words, the device is on a cellular network that is not the home network, and therefore it's being charged higher rates. Often your app will not care about this and just leave it up to the user. But if your application is working with large amounts of data, then you might consider being kind to the user and letting them know that it's going to be expensive to continue. We can detect roaming connections through the same classes we've been using either the isRoaming property on Android or the isCellularDataRoaming on Windows Phone. Now, what we've done up to this point is work with the platform-specific APIs. And if you wanted to incorporate this type of logic into your Xamarin Forms app, you'd have to provide an abstraction and write the platform-specific code to adhere to that abstraction. Luckily for us, this work has already been done in a NuGet package named xam.plugin.connectivity. You can view the source through the link shown here on the slide, but we'll use this component in the lab in just a moment. The last thing we want to point out is once we know we have a network connection and our app is ready to use it, we often want to let the user know when it's active. We can do it through some custom UI. We'll do that in the upcoming lab exercise. But on Xamarin Forms, you can also use the isBusy page level property to display an operating system specific busy indicator. This is useful if the network I/O you're doing is background operations. However, if the UI is blank while you retrieve data, you should probably put up something a bit more prominent. Okay, so now we're going to take a flash quiz. And this is just meant to reinforce the knowledge that we've talked about and prepare you for the Xamarin University certification exam. I'm going to put the questions on the screen and read the questions. I want you just to answer to yourself as we go through the questions. Question 1. You can add code to monitor network connections directly in a shared project or portable class library. Is that true or false? And that's false. Our network connection code is going to be platform specific. We'll need to abstract that out. Question 2. To determine if an iOS device is roaming, you need to A. Check the isRoaming property on the Connectivity Manager, B. Subscribe to the Reachability Changed event, or C. You cannot detect roaming conditions on iOS. Unfortunately, iOS does not give us the ability to check if we are on a roaming network. Android and Windows Phone give us this capability, but iOS does not. Question 3. You can obtain network information about an Android device using which method call? So A. Get network information, passing connectivity type.mobile. B. Get network info, passing connectivity type.mobile. Or C. Get network type, passing connectivity type.mobile. There we're going to use get network info, and we're going to pass the connectivity type.mobile. This will give us the network information for Android. Now we're going to work on an individual exercise. Here we're going to determine the network connectivity for each platform. If we open the lab materials, start here, included in your download, and we scroll down to exercise 1. This exercise is meant to take about 15 minutes. You can take as long as you need during this video. If we scroll down, we can see the steps here. And you're going to create a new Xamarin Forms application, add the connectivity plugin from NuGet, and determine the different network status information for each platform. Now, we'd like you to pause the video, work on that individual exercise, and then continue the video when you are done. In this first exercise, we took a look at how we can determine whether our device is connected to a network or not, and if we're able to reach a certain URL on the network. We did this by first adding the Xamarin Forms connectivity plugin to our projects so that we could check our network status within our shared code. And then we added 2 pages to our application. The first page will allow us to ping specified URLs and make sure that they're accessible. Let's go ahead and run our application, and we'll watch this in action. When the app first starts, we're going to wire up the connectivity plugin's connectivity changed event, and we'll listen for when our connection changes. And let's start out with our network page here. We can use the network page to ping certain URLs. Let's try Xamarin.com, and we'll use the plugin's isReachable method to ping that URL. This brings us back a Boolean whether this URL is available or not. In our case, Xamarin.com is available. And we can update our page. And then we want to listen for that connectivity change. What happens when we lose our connection or our connection reestablishes itself? An easy way to test this in the iOS simulator is to simply turn off the Wi-Fi on your machine. There we get the connectivity changed event raised. We're able to listen for that, and we can switch the page that we're displaying to our no network page. And by turning the Wi-Fi back on, we'll get that event raised again as soon as the Wi-Fi connects, and we can switch back to our network view page. Now, before making any network calls, it's important to check your network connection status to avoid timeouts or exceptions. And you can see how we can do that in our Xamarin Forms projects here using the connectivity plugin. In this first objective, we've now seen how we can determine if our device has a connection or not, and if so, what is that connection type? We've also seen how we can listen for network change events and respond accordingly. Our goal for this session is to explore accessing REST-based services. But there may be some of you who haven't done much with REST before, so let's spend a few minutes and cover the basics to make sure that you understand what a RESTful service looks like and how to interact with it. We've got 3 goals here. First, we're going to identify where REST came from and what makes a service RESTful. Second, we'll talk about how URLs are used in REST. And finally, we'll talk about a few guidelines for consuming and utilizing REST services in your apps. REST is short for Representational State Transfer, and it's really more of an architectural description than a technology. It was originally coined in a PhD dissertation by Roy Fielding, who is one of the original architects of the HTTP protocol. Mr. Fielding was doing research on the scalability of the internet and noted that existing web services did not benefit from the architecture of the World Wide Web, but instead tended to be oriented more towards traditional RPC, or remote procedure calls, style definitions. He described a model where the services could leverage the high cacheability and location management to achieve a much higher level of scalability over existing architectures, specifically over SOAP, and referred to it as a RESTful model. The architecture of a REST-based service is really defined by 2 things: HTTP verbs, which indicate the action being performed, and uniform resource locators, or URLs, which identify the resource to perform the action on. Since its introduction in 2000, REST has become the dominant architectural style for exposing services over the internet. And this is primarily because it's much easier to consume on the client side, making it fairly trivial to use services from JavaScript and client-side scripting. As of 2012, REST comprised of almost 75% of all the public APIs on the internet. SOAP was a distant second at 20%. SOAP tends to be more useful on closed networks or private services utilized within a corporate domain, which were not considered in this study. Most public web APIs these days expose both SOAP and REST, and generally encourage clients to prefer the REST interface. So let's talk for a moment about how you access a REST-based service. To start with, REST is oriented around the HTTP verbs or operations. We can use GET to retrieve a specific resource. The body of the response will contain the requested resource. We use POST to create a new resource when the location or the ID of the resource will be determined by the service upon creation. The body of the request will contain the resource to create. The response body will often contain the newly created resource with the assigned ID, or the URL to retrieve the newly created resource. We use PUT to update an existing resource, or to create a resource when the client determines the location or the identifier. Again, the body of the request would contain the resource. And finally, we use delete to remove a resource from the service. There are other HTTP verbs, such as option, head, and trace, which are also usable with a REST service, but these are fairly uncommon in the real world, and the 4 verbs you see here are the ones you will consistently be concerned with. The second part of a REST service is identifying the resources. Unlike SOAP, which includes the identifier in the XML body of the request, REST uses the HTTP URL to identify the specific resource to work with. For example, when we request a resource using GET, we identify the specific resource through the past URL. Here on the slide you can see we're retrieving a specific customer with an ID of 12345. Either approach shown here will be valid to get the customer, and many services will actually accept either one interchangeably. The path to the resources controlled by the service is very consistent when using REST. You can bend the URL to include search terms, relationships, and even different data representations by changing the structure of the URL. Another key aspect of REST services is that they utilize just the normal HTTP response codes defined by the HTTP specification. For example, if the resource is valid and can be found, we would get a 200 OK response with the body of the response containing the resource. If the resource cannot be found, we would get a 404 not found error, and if we can't access the resource due to a security reason, we should get a 401 unauthorized or a 403 forbidden. Again, the concept is simplicity and consistency. These are well-known codes that already are understood by the browser and the web infrastructure that we're depending on. The response body contains the requested resource, but the format of that resource is not defined by the REST specification. Instead, it's up to the client and the service to decide that together. Again, the HTTP specification is relied on for this exchange, with the content type header indicating how the body is formatted. In this case, as you see here, it's going to be XML. The body is then just the resource itself in the content format. Again, XML in this case. There's no additional wrapper around the data, nor any defined structure to the data. That's completely up to the service to define. This is both a strength and a weakness. REST services tend to have much smaller payloads than the equivalent SOAP structure, which makes them easier to work with and much faster to deliver and parse on both sides. However, the lack of a defined structure means that the client needs to know what the data format is prior to calling the service. When working with REST services, or actually HTTP itself, there are two important concepts to be aware of: safety and idempotency. An HTTP verb is safe if it does not modify the resource. This is actually what allows the high scalability of the World Wide Web and of REST services. Because the verb is safe and the data will never change as a result of the call, the response can be cached. This caching can occur on a middleware client, on a proxy server, on the browser stack itself, or on your ISP servers, or on the remote server. And this dramatically increases the performance and the scalability of the services themselves. This feature is, in fact, what keeps the internet from falling over due to high load. Your ISP caches off the really high demand web pages and returns a local copy back to your browser instead of sending the request all the way to the real server. On mobile networks, the carriers will often perform caching of data to improve latency and decrease the network traffic that they have to carry. Because REST services depend on HTTP, GET requests to retrieve resources are also cacheable based on the URL identity. This is also the downside of SOAP services. They all use the same URL for every operation, and they use the post verb, and therefore they can never be cached and they must always be processed by the server. Idempotency is the other key feature of HTTP. An idempotent verb simply means that you can send the request more than once without affecting the state of the server. That means the state of the server is always consistent, even in the face of multiple identical requests. The one that always surprises people here is delete. In the case of delete, the resource no longer exists no matter how many times you send the request. You can certainly fail the request with a 404 not found, for example, or you could return an error, but that doesn't affect the idempotency of the method itself. So the return result doesn't have to be the same every time, just the results on the server. This makes error recovery more predictable for the methods because we can resend a request without worrying about side effects when we get a timeout, for example. REST, unlike SOAP, does not put as much structure around the payloads. As a result, you can often request different data formats from a service. And when this is the case, you should prefer JSON. If you don't know what that is, hold on, we're going to talk about that in detail. As I mentioned, REST utilizes the HTTP status codes to report the outcome of a request. Pay attention to these result codes. They will tell you when resources are valid, have moved, or are unavailable. Finally, REST implies that you utilize the URL to identify the resource, meaning that once I know the URL structure for one resource, I can easily locate others without documentation or additional help. And that you follow the HTTP spec. So post is used to create an item, put is used to update an item. And often services do not completely adhere to these ideas. We often still call them REST-based, but when they break these sorts of rules, they don't really behave like a true RESTful system, and therefore are sometimes classified as JSON over XML or HTTP instead. This is becoming less common as people understand the guidelines for a true REST-based service, but you really need to read the service documentation to really see the expectations of the service and how to identify and interact with the resources. Finally, something we need to touch on is security. Unlike SOAP, which has a broad set of specifications for a variety of additional requirements, REST doesn't have any specification for security. It's really up to the service to decide how to authenticate, authorize, and secure the data being used by the service. That said, you should always prefer HTTPS to communicate with the service if possible. This will encrypt the data going peer-to-peer using the transport level encryption. In addition, many services use OAuth for authorization, and Xamarin has a component called Xamarin.auth, which has support for that if you need it. This will allow your client to log into the service through a trusted party, such as Twitter, Facebook, or Google. Another common spec is OpenID, which is used for authentication, and supports using a single ID to log into multiple sites. This is useful when we want to identify who we are versus just that we are authorized to use the service. Now we'll take another flash quiz. Question 1. What HTTP verb should be used to update an existing record? Is it A, get, B, post, C. Put, or D. Update? In order to update an existing record, we will use the put verb. Question 2. One advantage of REST is that many operations are cacheable. Is that true or false? That is true. Cacheable services are one of the biggest benefits of using REST. Question 3. Which of these choices would potentially be valid to retrieve a resource with an ID of 1 and a type of fruit? Would we A. use the get verb on the URL you see there, B. use the get verb on the URL including the query string, C. use the get verb on the URL using food/fruit, D. post to the given URL, or E. all of the above are possible? When we want to retrieve a resource, any one of the get verbs would be valid. Also keep in mind that these are just possible URLs to access the resource. The actual URLs are going to be determined by the service. So we've now seen what REST services are and how to use the URLs in REST, along with some guidelines for using REST. Now let's get to the meat of the course and look at how to actually use a REST-based service from within your application. We'll explore this in 3 parts. First, we'll look at some alternatives when talking to web services from our mobile apps, just so that you know some of your options. Then, we'll talk about how to turn the objects your program works with into bytes that we can transfer to and from the network. And finally, we'll look at some specific operations we want to perform with our REST services. To start with, let's talk about the APIs you'll consume when building requests to send and receive from a REST service. First, we have the classes built into .NET. The latest iteration is HTTP Client. This is a very simple wrapper around the HTTP operations we've talked about. While we don't have it listed here, you could alternatively also use the HTTP web request, or even the low-level socket class if you wanted to. These are all built into the framework, which means they tend to have less impact on the size of your application. Because it's built in and popular, this will be the approach we focus on. But let me give you a few other options you can explore on your own. ServiceStack is an open source client-server framework for both building and consuming web services. It includes a PCL you can add to your project through NuGet, which provides a strongly typed client accessor. If the service you're consuming is built with ServiceStack, it might be worth exploring using the client library, as it enables 100% code sharing of the data objects passed back and forth. Another popular open source option is the REST Sharp library. This is a REST and HTTP client built for .NET, but also usable with Xamarin. It has support for uploading and downloading files through HTTP, cookies, various authentication mechanisms including NTLM, and both JSON and XML serialization. And last but not least, each of the platforms has a dedicated web service framework or HTTP stack built in, which you can use if you're focused on a single platform. Xamarin has full bindings for each of them. You can check out the vendor-specific documentation if you prefer to take direct advantage of the platform's capabilities. Just keep in mind it won't be portable. Now, as I mentioned a moment ago, HTTP Client is a built-in HTTP client library, and that's what we'll focus on in this class. It has support to construct the HTTP message, send it to a web server, and consume the results in an easy fashion using task-based APIs for performance, giving you access to the headers, the status codes, and the body of the message. HTTP Client is built into the platform and available to your Android and iOS apps directly, but it isn't included in the PCL profile. So if you want to use it in a portable class library and share your client implementation, you'll need to add a NuGet package for Microsoft, which enables the use of the library. This is also required for Windows Phone, which doesn't include an implementation of the library. Since we are doing network I/O, we must inherently wait for transfer and processing time. Given that this wait time is indeterminate, it makes sense that the HTTP client exposes all of its APIs as asynchronous task-based methods. This means we'll use the C# async and await keywords to utilize the library so that we can easily process the response on our UI thread, while taking advantage of the asynchronous nature of the I/O itself. In the code you see here, we're searching the iTunes web service for media related to Batman, and returning the response as a string to the caller. Let's look a little closer at the API model. Let's start with the most common operation, which is GET. Recall that we use the HTTP GET verb to retrieve data from a service. HTTP client has several ways to invoke this operation. Each of them take the URL as input. First, we can use the getStringAsync method, which returns the method body as a string. We saw this form on the previous slide when we invoked the iTunes service. This is the simplest API, and it's the most common one you'll likely use. Next, we can use the getStreamAsync. This returns the body as a .NET stream, so you read the data byte by byte as it's delivered from the network stack. This API is very useful for large datasets or file downloads, where you don't want to store the entire response body in memory at one time, but want to either process it in chunks or save it to some offline storage. We can also retrieve the response as a byte array. This is useful if the data is not text-based, is encrypted, or encoded in some fashion. And finally, we can retrieve the entire response as a complex type called HTTP response message, which includes the headers, the status code, and the encoded body. If you need access to non-body elements, then this is the API you're going to want to rely on. The other methods are really just nice wrappers around this method, which pull the content out for you. But you can work with this API directly if you prefer to have more direct access to the response data. Let's look at the structures behind this a little more closely. The HTTP response message class provides access to the entire HTTP response through various properties. In particular, there is a status code property, which has the HTTP status code, and an isSuccess status code property, which makes it really trivial to verify that the response code falls in the range of successful responses. You can access the received header information with the headers property, and the class includes a content property, which gives you access to the body of the response as another complex type named HTTP content. HTTP content provides a wrapper around the HTTP body and supplies some methods to read the data as a string, stream, or byte array. This is also the object we'll create when we're creating a POST or a PUT request and need to supply a body to the HTTP request. When we transfer data to and from the web service, we'll need to turn our object graphs into something that can be transmitted over the network connection. We call this process of turning our in-memory objects into data streams serialization, and the reverse, where we take the network data and turn it back into objects, is called deserialization. And depending on the framework you're using to communicate with the service, this process will either happen transparently or directly in your code. When talking to REST-based services, we have two primary formats that tend to be used: XML and JSON or JSON. Most services support both and will decide which to return based on the client type or the value of the accept header, which is part of the request. You've probably heard of JSON. It's a textual serialization format which turns properties and fields into key value pairs. It's easy to parse and natively supported by JavaScript, which is where it was originally introduced, as you might have guessed by the name. JSON has quickly replaced XML as the preferred serialization format, primarily because it tends to be more compact and easier to parse, which translates to better performance, particularly on scripting platforms. In the example on the right side here, you can see an array of contact objects expressed in JSON with name and email values. As we talked about a moment ago, the server side will often decide what format to send the client based on a couple of factors. One of those is the value of the accept header. As the client, we can request an acceptable response type using the standard HTTP content types as the value. Here, we are setting our accept header value to application/JSON, indicating that we'd like to receive the response as JSON. You can add multiple values separated with semicolons to indicate secondary preferences, for example, text/XML, if we could also parse XML. We would then have to examine the returning content type value to know how the server formatted the data. If you do not include an accept header, then the server will assume you can accept anything and send it whatever format it prefers. And finally, if the server doesn't support the specified format for the data, it should return a 406 not acceptable response. Once we've got the data, now we've got to parse it. You could, of course, just do your own text parsing if you prefer. However, there are two popular libraries which do the heavy lifting for you. First is system.json, which is Microsoft's original JSON library. And this library, much like HTTP client, is part of the platform profiles, but not available in PCLs. It provides a simple wrapper around JSON, and it gives you some basic building blocks for working with the format. A much more popular choice is JSON.net, which is an open source library that provides a full typed wrapper around JSON for serializing and deserializing data. This is a third-party edition, but it's fully supported on all platforms, including PCLs. It has become the de facto standard, and it's the one we're going to use in the lab exercise. In fact, Microsoft now includes this library for ASP.NET projects. They don't even use their own JSON library. Of course, if you're using a different REST library, like REST Sharp or Service Stack, it will likely include its own serializer, so keep that in mind. As you probably expect, JSON.NET is a NuGet package which you will add to your shared code project, and also to your platform-specific project, so it's bundled with the application. Once you've decided on a JSON library, you'll need to create your data objects used to transfer information. We often call these data transfer objects, or DTOs. Unlike SOAP, which often includes a description of the data, when working with REST, you have to know the shape of the data and create the mapping between your objects and the JSON or XML data. In this data presented here, we have an array of contacts. And each contact includes a name and an email address. And to use JSON.NET with this, we would need to define a corresponding class to include this data. JSON.NET maps public properties using the name, generally ignoring the casing. So to map our email and name, we would create a class with two properties using the same names with types which can hold the data, in this case strings. We would then also need a class to hold the array itself, which has the name contacts, since that's what JSON.NET will be looking for. You can, of course, do this conversion on your own given a sample of the data, but there are a few nice online tools which will do this translation for you. Here you can see two such tools to look at after the video. So back to our GET operation. We would issue the GET_string async request using HTTP client and take that string response and run it through JSON convert.deserialize, which is part of the JSON.NET library. Notice that this is a generic type, which returns our strongly typed class for us. At this point, we have a set of C# objects to work with. The other operations are similar. We have methods on HTTP client to asynchronously perform a post, put, and delete. Unlike the GET operation, we don't have a lot of variations and only have one method with different parameter overrides for each one. There's a lot of code here, so let's step through it. The steps for using these methods are to create the HTTP client and then create the body of the request. Remember, this is an HTTP content object. We will typically use a derived class to create that content. Here we're using a string content object, which creates the body from a string. Again, we use JSON.NET to serialize our data, and this time also including the encoding type and the content type for the message, which would be application/JSON. And then we'll call the appropriate API, put async, post async, or delete async, and pass it the URL and the content object. We can also add headers here if necessary through the default headers collection. You saw some code that did that earlier. These methods are all asynchronous, and they return a task of HTTP response message, which we can then await. And finally, we process the response by checking the status code, and if it's successful, deserializing the body back to an expected object by reading the content out as a string. Different HTTP operations will return different results, so the processing code will likely be unique to both the operation you're calling as well as their expected response. So let's get some practical experience with a flash quiz and a lab exercise. Question 1. REST is an architectural style based on A. HTTP and XML, B. TCP/IP networking, C. the World Wide Web, or D. none of the above. REST is a style built on the foundations of the World Wide Web, with the HTTP verbs and the caching infrastructure of the web. Question 2. One way to send HTTP requests to a REST-based web service is A. HTTP content, B. HTTP web client, C. HTTP client, or D. HTTP request. So HTTP client is the class that we're going to be using to make all of our calls to our remote REST-based web service. Now let's work on individual exercise 2. In this exercise, you'll modify a basic Xamarin Forms application to add support to use an existing REST-based service and work with the return data. The UI has been created already. You'll be filling in the server access code. Please pause this video and complete exercise 2 in your materials. Let's review the code for our book service application. In this exercise, we saw how we could use the HTTP client and JSON.NET NuGet packages to make accessing a REST-based service and working with the results very easy. Again, we're using the Xamarin Forms application here, and all of our network access code is located in the Book Manager class, as you can see here. Here, we're going to use the getClient method to create our HTTP client, get a unique authorization key from the remote service, and add our default headers. The headers tell the remote service who we are and what data formats we would like to have returned. In the getAll method, we will perform a get operation on the remote service to retrieve a list of books in a JSON format and then deserialize them into objects that our UI can display. In the add method, we'll create a new book object, serialize that object into JSON, and post the data to the remote service. Let's see this in action. Here we start with an empty Xamarin Forms page. Let's go ahead and put a breakpoint in the Get client, and we'll click Refresh. The first thing we're going to do is come to the getAll method, which is going to need to go get our client. The client is going to see that we don't have an authorization key yet for this service, so it's going to call out to the login resource, which will return an authorization key for us. We're going to save that for all subsequent calls to the service. And then we'll add our default request headers of authorization, passing back the key that we got from the service, and our accept header saying that we want to have JSON returned to us. The service now returns that list of books for us. Now let's go ahead and add some breakpoints to the add method. We'll click add here. In this case, because we're creating a new book, our ISBN will be generated, and we'll add the book. This comes to our add method, where we create a book object. Again, we're going to call out to the getClient method. We already have an authorization key, so we didn't need to go get a new one, but we still need to add that authorization key to our headers, and we need to add the accept again. And we'll call the post async, which is then going to return our book for us, including the ISBN number. And now we have our Easy Xamarin development. If we click that, we can see at the top we had an ISBN number assigned to us. In this objective, we saw how to use the HTTP client to connect to a REST service and call operations on the service, and how to use JSON.NET to serialize and deserialize our data. The last topic we want to cover is some quick optimizations you can do which will improve the performance and platform integration of your HTTP client code. We'll look at two quick topics. First, how to customize HTTP client, and second, a customization you should strongly consider adding to your code. HTTP client was designed to be extensible, and to that end, it supports passing in a message handler which can affect how it transfers information and deals with common HTTP scenarios. Microsoft included a built-in message handler called HTTP Client Handler, which lets you customize some features of HTTP Client. You can turn on redirect support, so HTTP Client will automatically redirect a URL when it gets a 300 response, 301 or a 302. You can also turn on whether it supports using the system proxy, how it deals with the compressed data in the body, and whether it supports HTTP authentication. To add customization, you create the handler and then pass it into the constructor of the HTTP client. When dealing with the iOS and Android platforms, HTTP client has a few deficiencies. Specifically, HTTP client is a managed implementation, so it's completely unaware of the native platform networking stack. As such, it's not as efficient as the native implementation that's built into the operating system. As a result, some things won't leverage the platform properly. For example, if the cellular data is turned off, HTTP client won't attempt to turn it back on. We can fix these issues, however, using the extensibility of HTTP client. First, Xamarin iOS includes a message handler which causes HTTP client to use the native CF network stack. And this means it uses the iOS network connection pool, it relies on native threads instead of managed ones, and it works like a native application would when dealing with the network. You enable it by passing the CF network handler class into the constructor. Now, this is a platform-specific option, so you would need to abstract this out if you're sharing the code. Now, if that sounds like something you would like to do, then you'll love this. Paul Betts created an awesome open source project that you can add to your project with NuGet, which adds a highly performant message handler for iOS and Android that leverages the native platform networking stacks on each platform. On iOS, it uses the NSURL session library, and this is a higher level library built on top of the CF networking stack. So you get all the same benefits of using the CF network handler that I just mentioned. On Android, it uses the OK HTTP networking stacks, which integrates with the Android operating system. It supports silent network recovery, auto switching from cellular to Wi-Fi, and fallback negotiation for TLS or SSL. You absolutely must add this add-in if you're using HTTP client, and it turns out to be really simple. It's just as simple as adding the NuGet package to each of your projects. And then you'll simply add a single line of code into your application. In fact, this code can be done in the PCL. The NuGet package automatically does the abstraction on a per platform basis for you. So this one line of code is all you need to get the benefits. Let's give it a shot with our exercise. Adding modern HTTP client is very simple. Here we're going to continue with the same solution we've been working on, And we're going to come up to our book client, which is our PCL, and we'll click Add Packages. This is going to open the NuGet Package Manager for us. And here we can search for Modern HTTP Client. In our results, we'll choose the Modern HTTP Client NuGet package and choose Add Package. And now, the only change we need to make to our code is in the line where we actually create our HTTP client. We'll add a using statement, and when we pass into the constructor, we're going to pass in our message handler. In this case, this is coming from the Modern HTTP client, so we can say new native message handler. And once again, we can run our application. The functionality of the application is going to be exactly the same, but now it's going to be using the much more efficient networking stacks on iOS and Android. And there are our results. This is a very simple optimization you can add to all of your Xamarin-based apps or Windows Phone-based apps to get a much better networking experience. With this exercise, we've now seen how to leverage the more optimizing networking stacks on each platform by adding the Modern HTTP Client NuGet package to our projects. Thank you for watching Consuming REST-Based Web Services with Xamarin University. If you have any questions about the material, please post a question in the Xamarin University forums or schedule some office hours to speak with an instructor. Happy coding!